Good afternoon, everyone. Hello and welcome here in the Blauwe Zaal to this Studium Generale lunch program on the quantum computer revolution. Great to see so many of you interested here today. And for some of you, it might have escaped your notice. I wouldn't blame you, but this year is the International Year of Quantum Science and Technology, officially decided by the UN that this is the year that it's been 100 years since the first development of quantum theory. And a lot has happened during that time. And it was only yesterday that the Nobel Prize for Physics went to 3 scientists who in the 1980s worked on quantum computing, and their discovery helped pave the way for a new generation of quantum chips. Well, they're not only in all our phones in some way or other, but quantum chips are also important for the much discussed quantum computer that will have enormous computing power once it comes into existence. Now, it can be a challenge to intuitively understand the principles behind quantum mechanics. And it's especially hard to imagine how a particle can be in 2 states at once. Yet this principle is one of the key aspects of the technology. Now, today's speaker will help guide us through the world of qubits, of entanglement, superposition, and other quantum properties, so that in the end we will all understand some of the basics of quantum computing. Now, it was announced that Dr. Annemarije Zwerver would be our speaker for today. Unfortunately, she could not make it, but we're very happy to have a substitute with us who is also a TUE graduate. Sjoerd Loenen, he did a Master in Applied Physics here at TUE, and he obtained his PhD at QTech in Delft. He's currently a quantum hardware engineer in a quantum startup in Delft. And he will tell about the principles of quantum technology as well as some of his own research on lattice defects in diamond and how that relates to this quantum research he will tell you all about. So please welcome Sjoerd Loenen.
Hey all. Thanks a lot for the super nice introduction. And as was stated, quantum technology is governed by a few very abstract but super nice physics principles. And today I will be the one that hopefully can guide you through these principles and make you understand them in a bit of a better way. So what we're going to discuss today is quantum technology, and specifically the immense computational power and fascinating physics that is governing this quantum mechanics. And right now, you guys have actually picked a super nice time to come to such a talk. Since 3 years ago, as well as yesterday, the Nobel Prize has been awarded to topics that relate directly with the talk that you're going to listen to today. And I will discuss how these 2 Nobel Prizes link to the quantum technology that you will see today. You might ask yourself, why are we actually listening to quantum technology? And one of the key aspects, what you can look at why technologies are perceived as important, are governmental investments in technology. Because governments want to remain autonomous, to have certain technological power in the future to be withstanding geopolitical powers. As we also see right now that we are very dependent on China and the US for chips. So governments want to avoid that situation for potential future technologies. So if you look, the US has invested $1 billion, Germany has invested close to $1 billion, also Russia, China, and also the Netherlands. They have all invested a lot of money into this technology, which gives us the idea that indeed this technology is important. Looking ahead to the future, there's 2 big players that also make forecasts, and these forecasts show 2 things. One is that these numbers are ginormous, so they expect to have a lot of investments into quantum technology, and second is that these 2 numbers are very different. So it's still quite unclear what this technology will actually bring to us. And this is also what we hopefully will discover today a little bit. And so how we will structure this talk is that I will first discuss some basic principles for you guys to understand, hopefully, how this quantum mechanics ties into exponential computational power. Relating to that, I will then discuss what is the current state of the art, where are we now, and how long do we still need before we actually have such a device that can deliver on this promise of the quantum mechanics. And in the end, I will discuss something of my own PhD research and how we are sort of building on top of that to go towards the future. And so we will be discussing this quantum mechanics, but where can you actually find this quantum mechanics? Well, if you look at the world around us right now, you won't really observe it. But when we start looking at very small scales, so when we zoom in to about 1,000 of a millionth of a meter, then we start to look at the size of atoms and molecules, the fundamental building blocks of our world. And if we then zoom in into such an atom, this atom consists of neutrons, protons, and electrons. And these particles are so small that they are described by a fundamentally different physics than we know in the world around us. And this is called the quantum physics. And so an electron is such a particle, and with this electron, we can build quantum technologies. And for that, we need to be able to manipulate this electron very well. And so this electron you can actually envision as some sort of very tiny magnet that can point up, which we call spin up, or can point down. And you will see that this electron can actually point up and down at the same time. But the ability to build quantum computers comes down to being able to control such quantum particles like an electron with a very high degree. And so what we will do right now, we will go through 3 principles of this quantum mechanics, namely superposition, the quantum algorithms, and entanglement, which form the basics of how you can build a revolutionary technology. But before we go into that, I have a riddle that I want you guys to solve. And this riddle relates to immense computational power, and it goes as follows. In Delft, where I did my PhD, there is the 1+ highest church in the Netherlands. And I want you to build a tower using paper that is as high as this church. And the rules are that you need to do this very efficiently, so with the least amount of actions. Furthermore, this tower is about 108 meters 75 high. The A4 paper is 1 millimeter thick. You have unlimited paper to your availability. If you have a tower, it won't be falling down because of the wind. If you want, you can fold the paper as many times as you want, and if you want, you can also torn apart a piece of paper as frequently as you like. So I would like to invite you guys all to discuss for 20 or 30 seconds with yourself or with your neighbor to think of how you're gonna build this tower, with the caveat that you want to do this with the least actions possible. All right, let's gather once again. I've heard a lot of noise and rumors, so I bet probably some people have thought of it and might be able to give me an answer. Who would be up for the challenge? Yes? Exactly. So who else was thinking about folding the paper? Okay, this is of course a very intelligent crowd, because that's actually the right answer. And to elaborate a little bit, if you start stacking the papers, you'll need more than 100,000 actions. But if you start folding the paper, you have any idea how many times you need to fold? It's indeed 17. So we see that with folding only 17 times, you'll get to the height of this tower. And that means when I ask you the question to make a tower that is twice as large, if you would take the stacking idea, you would be stacking 200,000 or more actions. Whilst with folding, you only take one more action and you're there. And what this means is that this folding always gives you a factor 2 in output with only one additional input. And this is what we call exponential growth. And with exponential growth, you see that thus with 17 actions, I can get to the height of the tower. With 18, I can get to twice the height of the tower. And then we see with 39 times folding a piece of paper of 1 millimeter, I can get from here to the moon. What this demonstrates is that if you have something that responds exponentially to the input or to your resources, then you're in business. Then you can make very powerful technologies. And this is exactly what quantum mechanics allows you to do. Well, if you look at 100 years back, or actually before the start of really this quantum physics, everything we saw around us was described by Newton's laws. And that still holds in, let's say, the regular world we live in. That tells you when I push my gas pedal in the car, I will drive forward, unless you have the control in the reverse. However, when Schrödinger came along, he looked at the world with a different set of glasses, and he saw that actually when you look at these very tiny particles, you need to describe them with fundamentally different physical laws. And he came up with the Schrödinger equation, which definitely we won't be solving today. But once you solve this, you can actually see that this electron that I was speaking about can live in two things at the same time, two states. And this is commonly referred to in, let's say, popular literature as the Schrödinger's cat. And what the Schrödinger cat describes is that I have a box, and in this box there is this quantum cat. And since I don't look at the cat, I don't really know whether the cat is sort of alive or dead, the two states. And that means that this cat is dead and alive at the same time. This quantum cat has two states, being dead and alive at the same time. However, now what quantum mechanics also says is that when I start to open the box and I start looking at my cat, quantum mechanics will sort of pick one of these options for the cat to be in. So when I open the box, sort of the quantum mechanical property of superposition, that collapses to one of the states. And in this case, I've chosen to let the cat be alive, since I like animals and I think it's good to keep things alive. But what you see is that quantum mechanics allows you to be in a superposition state, but also when you start looking at the quantum mechanics, it sort of chooses one of the two states. All right, and how does this then tie into actual computations that you want to do with a quantum computer? For that, let's take a quick look at how computers like this one on the left of me do calculations. In this computer, there's billions of what we call currently transistors that can let a current through or can hold back a current. So let's say it has state 0 or 1, and these are the two states that you can have per transistor. And these we call computational units, we call them bits, and so if I have 1 bit, I can be either in 0 or 1. If I have 2 bits, I can either be in 0, 0, 1, 0, 0, 1, or 1, 1. And if I have 3 bits, I have 8 options, but still I can only represent one of these options at the same time. Meaning, if I have n number of bits, I can represent, let's say, this one number. If I now start to look at quantum mechanics, and I have this electron that can live in a superposition, so let's say not either in the north pole being 1 or the south pole being 0, but over the entire surface of the Earth, then it can live on the equator, for example, and you can be 0 and 1 at the same time. That means that for 2 qubits, I can represent all these 4 states at the same time, all these 4 numbers. And for 3 qubits, I can represent all the 8 numbers at the same time. And so for n qubits, I can represent 2 to the power n numbers at the same time. And this is exactly this exponential behavior that we also saw in this riddle. So this allows quantum computers to have an exponential character and compute very efficiently for some problems. So the conclusion is that contrary to normal computers, quantum computers have this sort of exponential behavior in them. Then a natural question arises is this quantum computer then actually always better than a regular computer? And here the answer is no, not specifically. And the reason is as follows. We again look back at this normal computer, and if I ask this normal computer to find the exit of a maze, how this normal computer would approach this, it sends its normal computing ladybug through the maze, and it can only send one ladybug. And every time the ladybug comes back, you ask the question, did you find the exit? Well, on average, it takes a very long time for larger mazes than this one to have the ladybug find the exit. So that's relatively slow. So in this quantum computing case, you can say, okay, I have this exponential behavior, so I can actually walk all these paths at the same time. And that's very nice, since then you can very efficiently find the exit. However, as we just saw in the Schrödinger's cat example, when you then ask the quantum computer for the exit, the quantum computer can actually only ask one of all these ants whether they found the exit. And then still you're sort of back to the regular computer, since you lost the exponential power because you can only target one of these ants. So the key thing to actually start using this exponential behavior of the quantum computer is that you need to find a way, an algorithm in mathematical sense, to make these ants sort of communicate with each other, and that when they all go to the exit, they sort of come back, they communicate with each other, and they all then start walking the same path that leads to the correct exit. And then if you only ask one of these ants, it will give you the right answer. So then you can actually use that exponential principle. So the conclusion is, the maze, or mathematically speaking, the problem you're looking at, should allow you to use this quantumness. So you need to be able to develop a quantum algorithm for your specific problem to use this superposition principle and the quantumness of your quantum computer. And this is important since this is typically not what you see in the news. They just state quantum computer will be exponentially faster, period. It really depends on whether you can actually develop an algorithm for this task at hand. Then there's the third principle that I want to cover today, and that's entanglement. And right now we've sort of looked at this single electron that can be in two positions at the same time. Well, I can have two electrons, they both can be in sort of two states at the same time. The purple and the blue one on the left, so they're both in a superposition, but they're completely uncorrelated. If you now start to look at entanglement, what entanglement prescribes is that you can have these two particles interact, so you get to the you take this globe again and you bring them together, and then they can have some interaction. For example, in this case, there are two electrons, so two tiny magnets. They feel each other's magnetic force. This allows them to interact and form entanglement. And what this entanglement is, without going very deep, is that they form super strong correlations that you cannot classically, with normal physics like Newton described, reproduce. And so what you see if you have this entangled state, then if I start to do a measurement on only the purple spin, then directly the blue spin will also be projected. So like I said, looking at quantum mechanics, we'll sort of take out the superposition. So now if I look at the purple one collapses to, in this case, spin up. That immediately makes the blue one also collapse to spin up. And if I then repeat the experiment, then I look at the purple one and it points spin down. When I then look at the blue one, it will always also point spin down. And Einstein called this spooky action on a distance because he thought, okay, well, if I measure the purple one, then there is some information traveling from the purple one towards the blue one saying, hey, blue one, I just point down, so make sure you're also pointing down. So what researchers then start to do, they brought them together to create this entanglement. Then they brought them, let's say, very far apart, so on the other sides of the globe, for example. And now we make two experimenters stay on these different sides of the globe, and they have a clock with them. And on very specific times, both of them are going to measure on these two spins. And if you repeat that experiment a lot of times, then you get a lot of statistics. And what you will then see that every time when I measure the purple one and the blue one at the same time, they will always correlate. So they will always give you exactly the same answer if you made this entangled state. So if you measure spin down, the other one will also measure spin down. And so this is what Einstein called spooky action on a distance, since now these two things are too far apart for the speed of light to actually cover that information transfer. And it turns out that this entanglement is also a fundamental aspect you need alongside this superposition to actually make useful quantum algorithms. And it was long sort of debatable whether this entanglement was even existing. And this is where the Nobel Prize 3 years ago was awarded to these three Nobel laureates that I was happy to meet in one of the conferences I went to and where they gave a super nice speech. And this also shows the importance of this physics aspect, this entanglement. And even later, in one of the research groups I was collaborating with a lot, before I was actually doing that, they published this impressive paper where they fundamentally proved the existence of entanglement, and there could be no sort of caveat underneath this. This was like 100% proof that it really existed, and thereby you could sort of say that they proved Einstein wrong. And what they did here, instead of going with these two particles to the other side of the world, they could separate them by 1.3 kilometers and thereby sort of mimic the distance of the world such that light wouldn't be able to pass through information. This entanglement, besides being very relevant to develop algorithms to use quantum principles in your advantage, it also serves as a fundamental source to prevent errors from happening in your quantum computer. One time more, I'll leap back to normal computers. Nowadays, these normal computers are extremely good, and most of the part can live without any error correction, since errors just barely occur in such a computer. However, back in the 1960s, when people were developing these normal computers, errors were occurring relatively frequently. So people came up with error correction methods. And the way they did this was, okay, I have this bit, let's say this calculation that I want to perform on this single bit. Well, I'm not just going to compute this calculation once, I'm going to do it 3 times. So I copy my exact computation and I do it multiple times. Then I do my computation and I see that in the end of the computation, 2 of my computations give me the result up, let's say North Pole, and 1 gives me down. Then the simple thing you do is you just make a majority vote. I see 2 of them are up and 1 of them is down, so the answer of my calculation is up. Of course, you can use more than three times a copy, but this is the fundamental idea. And so now quantum computers, these electrons that we need to control, we can control them pretty well, but still not exactly super well. So sometimes errors occur, and we need to be able to correct for these errors. And so then you might think, let's do the same thing as they did for normal computers, but quantum mechanics actually does not allow you to just copy the same computation. And so what is then the solution here? Now, the solution is to use this entanglement. And what you do here, you have, let's say, multiple error-prone qubits, quantum bits. And now you make entanglement amongst them, and that basically shares the information that was originally in 1 qubit over a redundant amount of qubits, so over multiple qubits. And that means that now you have, let's say in this case, 3 error-prone qubits that effectively form 1 error-free qubit. Since if an error happens on 1 of these qubits, information still also resides in the other 2, and using a smart protocol, you can retrieve this. And so the conclusion is here that this entanglement is needed for your quantum advantage, as well as for the ability to correct errors. And this error correction is really one of the big topics that the quantum community is working on right now, since errors is really something you should prevent in your calculation. So how does all this culminate to, let's say, some requirements that we need in order to build such a useful quantum computer? In the end, we need to have about 1,000 to 10,000 of these error-free qubits. And as we just discussed, we need a multitude of qubits to actually build up such an error-free qubit using this entanglement resource. And it turns out you need about not 3, but 100 to 1,000 error-prone qubits to build 1 error-free qubit. Besides, you also need to be able to manipulate these qubits, these electrons, with a very high degree for even all these protocols to work. So you already need to start out being very good, and then still errors occur that you then need to compensate using this entanglement. Also, this entanglement typically is created by interactions between these qubits. So actually you want this qubit on the right bottom to be able to also talk to the qubit on the left top. So you need to have a very large interconnectivity. And all these things are very big challenges. And let's focus now a little bit more on these top 2, which if you multiply them, you need to have around 10 million qubits, quantum bits, in order to build a useful computer. And so are we actually on track to get there? Well, to look at this, let's take a look at 3 of the larger quantum computing industries, quantum computing industry partners that are in this industry, which is Google AI, IBM, and IonQ. And Google is really leading the efforts on this error correction protocols. IBM is sort of leading the way in the amount of quantum bits, qubits they can implement in their quantum computer. And IonQ is more like a recently, like a startup that is a bit more recent. And actually right now it's very large, and even their stock value has gone up recently by a lot. And if we look at the prognosis of all these companies, then we see that right now, 2023 to 2025, they live in about the order of 100 qubits. So that's really a long distance from this 10 million that we need to get to. And actually all these qubits that they have, they're quite error prone, so they still need to reduce that. However, if we then look at the future, and specifically at the era of 2030 to 2035, there we see that these companies, they think that they can build quantum computers with about 1 million to 10 million quantum bits, with very high quality and error rates that are 1 in a millionth of a millionth. And this is really where we need to go to make these quantum computers solve useful problems for our society. And so I would also come back to the second Nobel Prize that was awarded yesterday to these 3 scientists. And these 3 scientists developed the principles, superconducting qubits, a certain type of qubit, that Google as well as IBM used to build their quantum computers. So they really did fundamental research about how you can use this physics principle, in their case quantum tunneling, to build quantum computers in a specific way. And this guy on the right, John M. Martinez, he was actually the one sort of starting up the Google Quantum AI Lab. And now Michel Devereux is the chief scientist of Google. So you see Google actually did a lot of efforts to sort of acquire scientists, also to build this quantum technology. And then you might ask, okay, nice, this 10 million qubits, but how does a quantum computer actually look? Does it look the same as my laptop here? Well, the answer is no. If you start looking at these quantum computers, how they look is that there's some sort of big data center, and in this big data center, there's a lot of equipment, and this equipment is actually expensive. It looks kind of like this. There's a company, Blue, for selling them. Cost is about $500,000 to $1 million. There's a lot of cooling power needed, since you cool these things down to nearly absolute zero to suppress all sorts of temperature noise. And you need to have very specific materials. Actually, even this company started investing $300 million to acquire helium-3 from the moon, whilst we cannot even acquire helium from the moon yet. So you see that for this technology to come to existence in a large scale, really a lot of new developments need to happen. Okay, so how does this Google and IBM thing relate to my PhD? Well, it's sort of in the same domain as quantum tech, but they build qubits, quantum computers based on a technology which is called superconducting qubits. There's a vast majority of types of quantum computers that you can build, and it's actually sort of a race which technology will be the best for eventually building a quantum computer. Might be a different technology that will be best for sensors, quantum sensors that might be very good. But in my PhD, I looked at a specific type of qubit in diamond, like Marley just said. And what this qubit is, it's actually a defect. So if you take a diamond, it's built up of very well-structured, periodically spaced carbon atoms. And now if you take out one of these atoms, then you create some sort of gap in the lattice. And it turns out that this gap in the lattice can capture an electron from the environment. And so now we have this electron there that we can then manipulate and build a quantum computer with. So how does that look? Actually, like I show here, this is the lab I was working in. It's an optical table of around 2 meters by 2 meters. And on this optical table, we have this small device here. And this device cools everything down to a temperature around colder than the universe, not as low as this millikelvin temperatures needed for these superconducting qubits, but still very low. If we open up this box, we see this PCB that allows you to guide electronic signals. And these electronic signals, they are needed to be able to control this electron. And so these electronic signals, they come in from the bottom. Then we need to sort of bond these pads towards the diamond, which we do with this line here. So this line is actually the electrical connection from the outside world towards the diamond that I was working with. And then on this diamond, you see this sort of track. This is gold, so we pattern gold on the diamond. And then this gold runs through these sort of holes that you see there. And if we zoom into such a hole, then the distance of such a hole is about 10 micron. And if we scan a laser over this hole, then this electron in this lattice defect will respond to this light, and it will send light back. And then we know that we found an electron. And if we zoom in this electron, then what we see is there's a vast majority of other quantum particles around this electron. And so using this electron, we can actually talk to a lot of other quantum particles that we can use to build a larger quantum computer than just a single electron. And this all happens in a space of around 3 nanometers by 3 nanometers by 3 nanometers. So 3 times 1,000,000th of a million to the power 3. So this is all extremely small, but you still see that we need a lab of around 2 by 2 meters to try to control these things. So then a question that is really sort of pushing the diamond community forward right now is, can we make this more scalable? Since if we in the end need to have a lot of qubits, we really need to get rid of measurement equipments in current research lab that are about 2 by 2 meters big. So the new developments in the quantum world is that we actually want to integrate this light that I was saying, not via bulky microscopes as I did during my PhD, but we want to integrate them using fibers. Actually, several very similar fibers that carry all the internet signals that you get to your home. And so what we need to do, we now need to make structures on the diamond to which we can sort of bind these fibers. So in this left picture, you see these 4 fibers coming in from the top, and we can sort of carve out a very specific shape in these fibers, then connect them to the diamond so that we can send light in from the fiber to the diamond, to our electron there, and then all the light, or part of the light emitted from this electron, will be guided back from the fiber, and then we can sort of measure what our quantum computer is doing. And what that means is that we need to carve out structures in this diamond so that we can actually make the light go there. And where do we do this? Where do we do this carving of the diamond? Well, here I show you a picture of the diamond sort of when we start fabricating this diamond. It's about 4 millimeters by 4 millimeters by half a millimeter thick. And then we take this diamond to the clean room, which is a very advanced technological room where you can do a lot of high quality processing on a lot of different materials. And in this clean room, which looks approximately like this is a very fancy photo of IMAC. We also have a clean room in Delft. You guys have here a clean room in Eindhoven, which is also extremely advanced. And a lot of processing of different materials is done there to make use of specific properties. And without going into a lot of detail, here's some sort of process flow that you need to do to build these quantum structures that we need for diamonds. And if you've ever seen a talk of, for example, ASML, it's extremely similar. They need to go through a lot of the same processes. And basically it comes down to having your diamond, masking it with a different material, potentially masking it with another material, then writing the structures that you want to have on your diamond, on your quantum chip, on there, and then you start etching it away. So etching is sort of carving out. So what you see sometimes when you go on holiday, there's these people on a stand selling these handmade elephants by carving out things from the wood. Actually, on a very small scale, we're doing exactly the same things here in a very advanced way. And if we do this, we sometimes need to make structures that are about 200 nanometers in width and then holes of about 50 nanometers. So we really go to nearly the smallest scales that we can think of and that we can image with the technology that we have currently available. So with these developments, we hope that we can sort of bring this diamond quantum community also to the future and do extremely cool things with this technology. But will we get there? That's still a question that will be left open for the future. And with that, I also want to wrap up. We have seen that we can find this quantum mechanics at very small scales. This quantum mechanics is governed by these principles of superposition that gives you this exponential behavior. Then you need to also have entanglement. This entanglement you need for these quantum algorithms as well as for error correction. You need to be able to actually find a problem where you can build a mathematical structure to use this entanglement and superposition. We also saw that you need to have around 10 million qubits, which will happen probably in a timeline of about 5 to 10 years. We saw that I used to work on very small pieces of diamond where you need very bulky structures to make quantum computers with these systems. And in the end, we see that we're now really making efforts toward more scalable technologies so that we're future compatible. And with that, I want to end this sort of seminar and leave the floor open for questions.
Sjoerd, thank you very much. Thank you for making this complex quantum world a bit more tangible. I think you gave some very insightful examples. And I'm curious to see if there are any questions in the room. Can be questions of clarification or something you would like to know more about. We have the catch box.
I see a question over there.
If you see it, Lenta, I don't... Yeah. Go ahead.
Hello. So they say that quantum computers are going to break like modern encryption that we have nowadays. And do you think that we should be worried for our data now that quantum computers are like in the future going to be accessible?
Yeah, so I think that's a very good remark. Indeed, one of the algorithms for which people have found that quantum computers can have an exponential benefit compared to normal computers is exactly, like you say, in the domain of data encryption. So right now, the data that we send is encrypted via a mathematical problem, factorizing a number in its prime numbers. And that is hard to solve for such a normal computer, but a quantum computer can do this very efficiently. So then to answer your question, should we be worried? I think the answer is yes. This is also what they call harvest now, decrypt later. So what can happen is that evil parties start to sort of harvest the data that you have right now, which is encrypted, and they can't do anything with it. But if this quantum computer comes to existence, then there is a potential that they can use this quantum computer to decrypt all your messages that they sort of steal right now. So yes, you should be worried, but also quantum mechanics gives you a way to overcome this. Quantum technology also has one sort of subdomain, which is called quantum encryption. And that type of encryption using quantum technology is fundamentally unbreakable. So that is one route that also quantum technology offers to sort of offset this agreeable, very negative side of quantum computers. That's one option. And the other option is that you can start thinking of post-quantum algorithms for encryption that even with a quantum computer, you cannot efficiently break. So it's not to say that the quantum computer per definition can do everything super fast. So there still is also a pathway there to start making yourself secure.
I think there's also a research group here at TUE working on that aspect, on the protection of future hacks like you.
Yeah, I think there's many research groups in detail.
Yeah, I know
and
at least one
likely,
here at TUE as well. I don't
Perfect.
know. Thank you for that question. Other questions? I see 2 over there. Okay, let's start in the middle and then we move on to you.
Yes, so do you actually get like an exponential speed up in terms of running time for most problems? Because as far as I know, there are a lot of problems where you get only like a linear to square root runtime speed up.
Yeah, so excellent point. So this relates to this this part of the talk where I was speaking about you need to have an algorithm to make use of this quantumness. And so this algorithm we just discussed, called Shor's algorithm, gives you an exponential speed up. But it's not given that this is there for every problem. So like you mentioned, for example, one of the examples is Grover's algorithm, where you need to search through a large database. And instead of doing a lot of random trials, you can get a quadratic or like an top power 2 speed up, which is useful, but not extremely useful compared to these exponential speedups. So to concretely answer your question, it really depends on the mathematical problem that underlies your, let's say, the thing you want to solve, whether you can start using this quantum computer for that specific problem.
Okay, thank you. If you can throw it to the person here in the front. Everyone watch out. Yeah. Won't be the first Catchbox accident.
Hi. Thank you for the presentation. And I had a question about diamonds. So you were referring to diamonds as probably we know of them today. And my question was, you gave an example how you use it in IMAC or people at ASML. I was wondering, do you use lab-made diamonds or natural diamonds? Or is there a difference if other ones will be used due to the chemical structure of the...
Yeah, that's an excellent question. That really goes more into, let's say, the details of what is important in this diamond for quantum technologies. And so you maybe mentioned ASML uses diamond. I don't think they specifically make these diamonds, but yeah, we use a lot of the same technologies like ASML to process these diamonds. These diamonds that we have, they are synthetically grown in very well-controlled labs to make sure there's a super clean diamond, since the diamonds that you sometimes hear of that are shiny, the reason they are shiny is actually that there is a lot of other atoms in that diamond, and these atoms give you this super shiny color. But for a lot of our purposes, we just want to have very clean diamonds. They're always transparent, and they're grown in labs. And even in Delft, we have made our own reactor where we can grow diamond. Just so you know, the rate of growth is extremely slow, so it's not...
It's very well protected.
It's very well protected
indeed. It sounds expensive.
Yeah. Well, yeah. So it's kind of interesting. A lot of people think that the diamond is the most expensive part, but for us, it's really the equipment around the quantum computer that is that's most expensive.
That's more expensive. Maybe to wrap up, Sjoerd, we currently live in a time where there's a lot of things happening with AI already. When you look at the whole ChatGPT development and all that, you're telling us today that in 5 to 10 years we will have this 10 million qubits that we need for the quantum computer. What should we expect? Like, how does the two tie in together? Is it going to be as big a development or like way bigger in 10 years?
How it sort of connects to AI, or specifically is...
Well, will it be like a similar... we used the word revolution in the title.
Yeah.
When do you expect the quantum revolution?
So in some sense, you could say it's already happening, since these technology developments that we have seen here, that we are building in Delft, Eindhoven, IBM, Google, they're really, really good. So they've made a lot of very impressive advancements. But still, there's 5 or 10 years more to go, and there's a lot of engineering challenges ahead, I would say. But once this computer gets there, I think we probably will be able to find a lot of problems where they are really useful, but it ties in a little bit to the second question we had. What problems are they going to be? I think it's definitely going to be some sort of revolution, relating it to how big the revolution is with AI right now. I think it's probably too early to make like any conclusive statements.
An educated guess.
An educated guess is, I think it's really impressive what is happening with AI now, and potentially also the ability that you get this AI that trains itself and potentially takes over cognitive processes of us. I think that's so incredible. So if you would need to make me bet, I think that maybe right now we're living in an even bigger revolution than that might occur with quantum technology. But to end, with a lot of technologies, you really never know how they work out. Also for AI, people didn't expect this to happen.
We will invite you back in 5 to 10 years to check up.
I'd be happy to.
Okay, thank you very much, Sjoerd Loenen. Thank you all for joining today. Thank you for your questions, and see you next time at Studium Generale.